Dear students, welcome to our online class, and the topic of this class is area of a surface of revolution. The first question is, what is surface of revolution? And these are some examples of surface of revolution. You see, if you revolve this semicircle or semicircular curve about this line, then you will get a solid sphere like this with empty interior. And if you revolve this line, this straight line about this line, then you will get a solid cylinder like this with empty interior. And if you revolve this line with this black line, then you will get a 3D material like this with empty interior. And again, if you revolve this curve with this straight line, you will get a material like this with empty interior. So we understand what is surface of revolution. And now the next question is, how can we calculate area of these surfaces like this? So here we have two formula in order to calculate area of a surface of revolution. And you see, if you revolve this straight line about this line, then you will get a cylinder like this, and this cylinder is nothing but like this with empty interior. You see, this is a cylinder, solid cylinder with empty interior. Now if you cut it here along a straight line, then it will look like this. So we want to calculate area of this rectangle actually, and in this case, so it's nothing but the circumference of this circle, and we know the circumference of this circle is 2 pi r, and r is the radius of this circle, and then the length or height of this cylinder, which is h. So the area of this rectangle means area of this surface of revolution will be 2 pi r and h. But the problem is, if your curve is not a straight line, in that case you cannot calculate the length of this straight line directly. You need to use a formula which we discussed in our previous lecture, the arc length formula, the length of a curve. So the calculation of the length of this straight line is very straightforward or easy, but this one is not. In that case, we know a arc length formula. So the area of this kind of surface of revolution is related to the formula of arc length. So finally here we have two formula 1 and 2. If your curve is like y in terms of x, and if you revolve this curve about x-axis, then this one will be your formula. You see, integration with respect to x from a to b twice pi y square root of 1 plus dy dx whole square. However, if your curve is like this, x in terms of y, and if you revolve about y-axis, then your formula will be the second one. And in this case, instead of y, you should write x, and instead of dy dx, your formula will be dx dy. So now the next question is, we want to understand where this formula comes from. How can we derive this formula? So now let us try to understand the derivation of this formula. The derivation of the formula for the calculation of area of a surface of revolution. We want to understand this formula, where it comes from. So let us try to let us consider a curve like this, y as a function of x, and if we revolve this curve about x-axis, then we will get a material, solid material with empty interior like this. And how can we calculate the surface area? By the help of integration. So first, if we consider a small band here, let us consider a small band like this, and how can we calculate this length? That we can calculate, the target is to calculate the arc length of this curve. So the first question is, what is the area of this small band? And the area of this small band, let us denote by sk, and if it will look like a circle, since you get this material by revolving this curve. So it will be a circle, and the circumference of this circle will be 2 pi r. Circumference will be 2 pi r. So the area of this small band will be 2 pi r is the circumference, 2 pi r times Lk. Let us denote this length of this small curve is Lk. So the surface of this small band will be 2 pi r Lk. And let me zoom this part here, and let us try to understand how can we calculate this Lk. And here let us denote this point by xk minus 1 and this point xk. So the change in x, let us denote by delta xk, and change in y, delta yk. By using Pythagoras law from this triangle, we can write Lk is equal square root of delta xk square plus delta yk square. And in our previous lecture, I explained these things clearly. This delta xk, delta y, how can we calculate delta y here? And slope, there is a theorem which is called mean value theorem. It says the slope of this second line will be equal to the slope of a tangent line somewhere here. Let's say this point is xk star. So if you draw a tangent line here, then the slope of this second line and the slope of this tangent line will be equal. That's what mean value theorem said. So mean value theorem said the slope of this second line, which is change in y divided by change in x, is equal the slope of this tangent line at this point xk star. And the slope of this tangent line is nothing but the derivative of this curve, derivative of this curve at x star. So which is derivative of fx at xk star. So from here we can write delta yk is equal f prime xk star delta xk. So let me put this result here, which is equal to 2 pi r, and this r is nothing but y, and Lk is equal to this square root of delta xk square plus delta y. Instead of delta y, let me write it f prime xk star whole square times delta xk whole square. So this equal 2 pi y root. We can take delta x square out of this square root. So I have 1 plus f prime xk star whole square dx or delta xk. So this result is nothing but the area of this small band. So now if we want to know the area of the whole surface, then we should add all xk for every small line segment. For every small line segment, we should add. So let us denote the area of the surface of revolution by S. So which is approximate to summation of all xk and k equal to 1 to n. And the more n you consider, the better approximation you will get in this case. So which is equal summation of k equal 1 to n, and sk is this. So let me write it here, twice by y root 1 plus f prime xk star whole square delta xk. So now in order to get the Riemann integral, we can put the limit on this delta x, and the moment you will put the limit on this delta xk, max delta xk tends to 0, the result will be equal. Instead of an approximation, now you can write S equal summation of k equal 1 to n 2 by y root 1 plus f prime xk star whole square delta xk. So now by the relation of Riemann sum and definite integration, we can write integration from x equal to a to x equal b twice pi y square root of 1 plus f prime x whole square dx. This delta x will convert it to dx. So this is our formula. You see, this is the same formula what we want to derive in order to calculate area of a surface of revolution. When your curve is like this, and if you revolve about x-axis, however, if your curve is like this, x equal function of y, and if you revolve about y-axis, then instead of y you should write x, and the integration will be on y, and instead of dx you should write dy, and f prime x will convert it to f prime y. So now let us try to understand our two formula more clearly by using these examples, and let us try to calculate area of the surface that is generated by revolving the portion of this curve. Which portion? Between x equals 0 and x equal to 1 about x-axis. So it says if you revolve about x cube, it will look like this. The curve will like this, and from x equal 0 to 1, so 0 is here and 1, let's say, is here. So we don't need these things. this curve is y equal to x cube, and this point 1 1. This is our axis notation. Now if you revolve this curve about this portion of the curve about x-axis, then you will get a solid material with empty interior like this, which will look like this. So we want to know the area of this surface of revolution, and since we are revolving about x-axis, our formula will be this one. The surface area is denoted by S, which is equal x equal a to x equal b 2 pi y 1 plus dx dy whole square root dx. So now here we are given curve y equal x cube. So d dy dx, our first derivative is 3x square. We can put it here, and the square of this derivative, let me write it here, which is equal, if you square it, it will be 9x to the power 4. So x equal a to b twice pi, you can write out of integration, and y is nothing but x cube. So x cube square root of 1 plus 9x to the power 4 dx, and a is from 0 to 1. Instead of a and b, I should write 0 to 1. You see, a is from 0 to 1. So we can easily integrate it by letting 1 plus 9x to the power 4 equals z. So the derivative of this one, 36 x cube dx equal dz. Therefore x cube dx equal dz by 36, and the corresponding value of z will be, when x equal to 0, z equal 1, and when x equal to 1, z equal 10. So this integral becomes 2 pi 1 to 10 root z x cube dx equal dz by 36, dz by 36. So this equal 2 pi divided by 36. We can take it, this 36 out of integration, and the integration of root z to the power half plus 1, 3 by 2 divided by 3 by 2, 1 to 10, and this equal 2 pi by 36. This fraction, if you take in the numerator, it will be 3 by 2 by 3, and if you put the upper limit, it will be 10 root z, 10 root 10, 1, minus, if you put lower limit, it will be 1. So this equal, if you simplify it, you will get pi by 27, 10 root 10 minus 1. This can be your answer, or if you want to approximate it, you can do that by using your calculator. That will be 3.56. Though 3.56 is the area of this surface of revolution if you revolve the portion of this curve from x equal to 0 to x equal to 1. So now let us try to understand our second formula by using this example, second example. And here our curve is this one, y equal to x square, and if we revolve this curve y equal to x square between x equal to 1 and x equal to 2, so we know when x equal to 1, y will be also 1, this point, and 2 will, this point is 2, 4. this point 1 1, and we don't need this part, we don't also need this part. Now if we revolve this, the portion of this curve about y-axis, then you will get a solid material with empty interior like this, which will look like this, and we want to know the area of this surface of revolution. So here our formula will be the second one, the surface area S equal y equal to C2 y equal to d twice by x 1 plus dx dy whole square root of square root dy. So this equal y start at 1 1 1 and end at 4. So 1 to 4 twice by x, and from here we can write x equal, we can convert this curve or write x as in terms of y. So x will be root y and square root of 1 plus, if x equal to root y, dx dy equal 1 by 2 root 2. So 1 by 2 root y whole square dy, and this equal 2 pi 1 to 4 root y 1 plus 1 by 4 y dy, which is equal 2 pi 1 to 4 4y we can take out of this the square root, then it will be root y divided by 2 root y, the square root of 1 plus 4y dy. So this equal pi into 2 and 2 will cancel, 1 to 4 and root y again will cancel, square root of 1 plus 4y dy, and let us consider 1 plus 4y equal z. So 4 dy equal dz, therefore dy equal dz by 4, and the corresponding value of z will be, when y equal to 1, z will be 5, when y equal to 4, z will be 17. So this integral becomes 5 to 17 root z dz by 4, which is equal pi by 4. You see, integration of root z is z to the power 3 by 2 by 3 by 2. So we can write 2 by 3 here, 5 to 17, and this equal 5 by 6. If you put the upper limit, you will get 17 root 17, and if you put the lower limit 5, you will get 5 root 5. This is your answer, or you can approximate it by using your calculator, that will be 30.85. So that 30.85 will be the area of this surface of revolution if you revolve the portion of this curve y equal to x square from x equal to 1 to 2 about y-axis. So that's all for the first part of this lecture 14, and hope you enjoy the lecture, and I hope I will see you in the second part. And in the second part I will again try to solve some other problems in order to calculate the surface of area of the surface of revolution by using our two formula. Thank you very much.